I will let you read example 4.5.15 on page 147, which shows you how we can factor a polynomial using nth roots of unity. It's kind of neat. I'll try to assign a homework problem like that based on that problem. I think it's interesting. But I need to get going into talking about PIDs, etc.
I think not including this week, because we have 3 weeks left.
Yep. Let's see your definition. A principal ideal domain aka PID, all right, is an integral domain I'll call it R, in which every ideal has the form A for some A. In other words, a principal ideal domain is a integral domain in which every ideal is principal. Theorem: if F is a field, then polynomials with field coefficients is a PID. All right. So this is one of those proofs that's like a good test question. There's a few of these in here. They're not entirely trivial, but they're good test questions. This is one of them. Let's go through it. So proof. All right, so we know f of x is an integral domain since f is integral domain. Right? We proved last time that polynomials with coefficients from an integral domain themselves form an integral domain because the product of two, the leading coefficient being non-zero, basically forces this upon us. So if I is an ideal of f, the polynomials over f, well, let's just say, not if, but like suppose, rather. Okay? If I equals to 0, then I is equal to the ideal generated by 0. So we're done. Okay, so the 0 ideal is principal. What else? If I is not equal to 0, right, then the degree of polynomials in I is bounded below. Hence, there must be a polynomial of least degree by the well-ordering principle. If we let, s equal to degree of f of x such that f of x is in I, right? Then this is a subset. Again, I have to throw out 0. 0 doesn't have defined degree, right? But anyway, this set is a subset of the natural numbers union with 0, right? So by the well-ordering principle, there exists, f of x in I with, least degree. Okay? And I'm going to call that, instead of f of x, I'm going to call that g of x, okay? I'm going to say let g of x be that element of least degree, okay? If f of x is an element of I, right, then division algorithm provides what? Q of x, a polynomial, such that what? Such that f of x equals to g of x times q of x, right? With what condition on r of x? With either r of x is equal to 0, right? Or the degree of r of x is less than the degree of the divisor here, which is g of x. Okay? Let me call those options 1 and 2 for the sake of discussion. We have two options. Option 1 or option 2. Note, r of x is f of x minus g of x q of x. F of x is in the ideal, and g of x is in the ideal. Therefore, g of x times q of x is in the ideal. So we're looking at the difference of ideal elements. That means that r of x is an element of the ideal, using the definition of ideal closed under, uber multiplication and subtraction. But then that's a problem, because then r of x is an element of an ideal of lesser degree, if 2 is true. So this rules out 2. By construction, right? Of g of x. G of x was the element of least degree. Well, it wasn't, I shouldn't say the element, I should say it's an element of least degree, right? There can be many elements of least degree, but this is one of them, g of x, and r of x cannot be non-zero in this division algorithm, otherwise it contradicts the least element property for g. Therefore, r of x is equal to 0. What's that show? F of x is equal to g of x q of x, which, by the way, is an element of the ideal generated by g of x. But g of x is an arbitrary element in I, right? So that gives us that I is a subset of g of x, right? I'd like to prove that it's a subset of the ideal generated by g of x. I say conversely, g of x subset of I is easy to see. Can you guys tell me why? I is an ideal.
Yeah, it's an ideal, but it's also a non-zero element.
Well, I is an ideal. I is a non-zero ideal.
Yeah.
But more than that, g of x is an element of I.
Yeah.
What is this?
The least
Well, this is
generated by the least element.
true, but more generically, this means multiples, polynomial multiples of g of x, right? But since I is an ideal, any polynomial multiple of g of x is again an I, because g of x is an I.
Yeah.
So essentially, by uber closure, this is a subset. By definition of ideal, that's a subset.
Wait, but if two sets contain each other, that means the sets must be equal.
That's right. Therefore, which is what we're trying to show. I is equal to the ideal generated by g of x. But I was an arbitrary non-zero ideal, we've shown its principal. So if it's zero, it's principal. If it's non-zero, it's principal. All the ideals are principal. That's the theorem for polynomials over a field. Now, if you don't have polynomials over a field, if you have polynomials over Z6, that's a non-starter because the definition of principal ideal domain is, first of all, that it's an integral domain. So we're kind of stuck there. You could ask the question, okay, so what if you looked at polynomials over Z6? Is every ideal in that? Does it make sense to talk about ideals when you don't have an integral domain? I think it does, right? We talked about factor rings. No, it doesn't. Well, if you don't have an ideal, wait a minute. I'm trying to remember. I don't think we insisted in our construction of factor rings that we're modding by. Well, we definitely have to mod by an ideal. But I don't know if the original ring has to be an integral domain. I don't think it did. No, certainly not. We can talk about Z6 mod like the even Z6s. That's an allowed construction. Z6 is not an integral domain, so we can talk about ideals inside something that's not an integral domain. So it might be an interesting question to ask. If you look at Z6, let me write it out rather than just blathering.
It makes sense that you could find an ideal inside of something that's not an integral domain.
So like this, such that ideals in Z6 are principal. I don't know, actually. I'd have to think about it. So it's just a question I'm throwing out there. Okay, next up, theorem. So theorem 4.5.18. If F is a field, and I not equal to 0 and ideal in polynomials over the field, and g of x a polynomial, all right, then I equal to what? Oh, okay. I equal to the ideal generated by g of x if and only if g of x is non-zero polynomial of minimum degree in I. So that's actually, this theorem is really a corollary to the proof here. That if you look at this proof, we've proved that. Right, this whole after I not equal to 0, if you look at this calculation, this argument, we have shown this result. A non-zero ideal is generated by the element of least degree. Now, a really nice application of this theorem, I'll show you now. Very nice, actually. Example. So if we look at the mapping phi from real polynomials to the complex numbers given by phi of f of x equal to f of I. Right? You can prove that this is a ring homomorphism. And so you can calculate its kernel, right? Moreover, you can notice that x squared plus 1 is an element of the kernel of phi, right? If we have f of x equal to x squared plus 1, then phi of, x squared plus 1 is equal to I squared plus 1, which is minus 1 plus 1, which is, of course, 0. So this polynomial maps to 0 under the map. It's certainly an element of the kernel. Is it an element of least degree in the kernel? How could you have lesser degree than x squared plus 1? You could have something of the form, consider g of x equal to ax plus b, right? If this was in the kernel, drop and give me 20. Sorry. That's going to be so out of place for people who weren't here. So v of ax plus b would then be ix plus b, right? Set that equal to 0. Can you, I've lost my a. Sorry. Good grief. ai, right? ai plus b. We put x equal to I. That's what the evaluate means. Can that be equal to 0? Well, the only way that can be equal to 0 is what? A equals B equals 0. You need both. For this complex number to be 0, it's only 0 if its real and imaginary parts are both separately 0. So what does this mean? There is no linear polynomial in the kernel. So the polynomial of least degree in the kernel of this mapping is x squared plus 1. That has degree 2, right? The degree of x squared plus 1, which is equal to 2, is smallest degree for poly in kernel phi, right? Thus, by the above theorem, kernel phi is what? It's the ideal generated by x squared plus 1. Can you tell me more? Can you prove that this polynomial, can you prove that this map is surjective? I think if you look at what I just wrote, we almost have a proof of surjectivity already, right?
Surjectivity is 1-to-1.
Is onto. So, yeah, like let B plus AI be an element of C. Then phi of what is equal to AI plus B? AX plus B, right? So this shows that an arbitrary element in the range, well, in the codomain, I should say, is mapped to by something in the domain. Therefore, phi is onto, which is to say it's surjective. But I prefer to write onto on the board, because surjective's got more letters. So then what? We can use the first isomorphism theorem. What's the first isomorphism theorem tell us? It tells us that R of x mod the kernel of phi is isomorphic to phi of R of x, right? Which in this case gives us R of x mod x squared plus 1 is isomorphic to C. There you go. We've proved this yet again. That real polynomials mod the ideal generated by x squared plus 1 is isomorphic to the complex number system. Es bueno? Well, I hope. I'll get out of the way. Sorry. So this proof, like, I had to write a lot, right? But if you really study it, the logic of it you can summarize in your mind in a couple of seconds, right? It's actually a very straightforward proof. And like many of the proofs here, it ultimately relies on the division algorithm, you know? So that's the end of my old lecture 25. It now brings us to lecture 26. Woo-hoo. Lecture 26 is really all about factoring. All right, so you guys know about factoring, you know, for a long time. FOIL, yeah. So we want to bump it up a notch, right? So first of all, definition. Let D be integral domain. We say f of x in polynomials over D, which is neither 0 nor a unit, and D of x is irreducible, all right, over D, if whenever f of x is equal to g of x times h of x, with g of x and h of x polynomials over D, then g of x or h of x is unit in dx. Right? A non-zero, non-unit element of D element of D of x that is not irreducible. By the way, that's the last time you'll see me write out irreducible. It will forever now be irrid. Not irreducible over D is reducible polynomial over D. Okay? Like this is, I think this is so far kind of like, this doesn't seem too far divorced from what you've learned in previous courses, am I right? I hope. Did you guys use the term irreducible? Maybe you, did you use the term prime? Prime polynomial? We'll make a distinction in those terms. So beware of that. We're not to prime polynomial yet. So example. And I forget what example I'm on. What example? Did you keep counting?
You did one before.
I'll do one again. I'm going to restart the counter at 1. Fine, 2. You happy? Okay. So this is technically example 4.6.2 on page 148, if you're keeping track. So the first thing to notice about this whole discussion, x squared plus 1, right? This is irreducible over the reals, but in contrast, f of x is x plus I times x minus I, so is reducible over the complexes. So a polynomial can be irreducible over one field and reducible over another one. Irreducibility is a, integral. It's a question of where you're taking the polynomial from. What do you allow as factors, right? If we're just studying the theory of real factorization of real polynomials, we're not allowed to do this thing of plus or minus I, right? It is forbidden. So another example. So by the way, I'm claiming that these are not units. So like, what are the units?
For what? Complex or reals?
For polynomials over a field, what are units? I should just, we should,
Building blocks.
the building blocks?
That's what I call them.
The building blocks. So I'll put it up here. If you have f of x, g of x equals to 1, how can that be achieved if f of x and g of x are polynomials?
Is there some, are we supposing anything, or there's any, like there any
Pretty much it has to be
non-zero?
a0, b0 equal to 1, and all the higher coefficients in f of x and g of x as polynomials have to be 0. So the units in the polynomials are just the constant non-zero polynomials. So like this, so here, well, it's kind of, what I'm trying to say is that x plus I is irreducible. That's something I can say in order to even enter the discussion of it being irreducible over C. I must first know that it's not a unit. But I know that x plus I is not a unit because the units, it's not a unit, right? The units look like u is just equal to like a constant, which is not equal to 0. Like it's just a constant polynomial. Those are the units. All right. It's important to know because we're always like on the watch for things not being units, right? So understand your foe. For polynomials over a field, you're just looking for a non-constant polynomial that makes it not a unit. So that's good. I mean, simple enough anyway. Another example, we could look at f of x equal to x squared minus 7, right? So, of course, you can factor this as x minus the square root of 7 times x plus the square root of 7, right? So this f of x is reducible over the real numbers, right? It's also reducible over the complex numbers because 7, square root of 7 and minus 7 are also complex numbers. So, all right. But f of x is irreducible over the rational numbers. Because you can't factor like that. It's not possible to factor x squared minus 7 just using rational polynomials. These are not rational polynomials, see, because they involve the irrational number square root of 7. Make a sense? Okay. Example 4. So here, again, we're going to consider f of x equals to x squared plus 1. And this time we're going to look at it as an element of z3 of x, okay? So notice that f of 0 is 1, f of 1 is 1 plus 1, which is 2, and f of 2 is what? 2 squared plus 1, which is 5, which is 2, right? So by factor theorem, right, there does not exist linear factor for x squared plus 1 over z3. So what is that? That shows f of x is irreducible in Z3x. Okay? What about, on the other hand, if we look at x squared plus 1 as an element of Z5x, is it still irreducible? What about there? Well, if you notice, f of 2 is 2 squared plus 1, which is 5, which is 0. So that means x squared plus 1 is x minus 2 times something. So apparently it is reducible, right? So here's an easy way to see how to factor this. Check this out, guys. So sometimes it pays to just like kind of bob. I mean, I have a calculation in the notes which kind of gives you a boring systematic method of kind of doing the calculation. But, you know, sometimes it's better to just do something a little bit sideways. How about this? This is the same as x squared minus 4, isn't it? Because mod 5, we can subtract 5. We're working mod 5. So it's actually the difference of squares. So x plus 2 is what you're looking for. That's actually the reduction. And of course, when you multiply this out, the minus 2x and the plus 2x cancel, and you've got x squared minus 4, which is x squared plus 1 working over Z5. Anyway, long story short, reducible, right? All right. So I've been kind of using this theorem. In some sense, I'm just, you know, proving the theorem in these examples. But I should just state it for our future reference and edification. And here it is, theorem 4.66. It's important to not overextend this theorem. It's very tempting to overextend this theorem. I have gotten very confused myself by overextending this theorem. F is a field. And f of x is a polynomial over the said field. And degree of f of x is equal to 1 or 2. All right, oh, excuse me, 2 or 3. All right, then f of x is reducible over f if and only if f of x has 0 in f. In other words, that there exists a in f, right, such that f of a equals to 0. That's what it means, right? To have a 0. So what's the proof here? All right, so let F be a field. And f of x a polynomial over that field with degree 2 or 3. if f of x is reducible, then f of x has linear factor. Do you see that? Think about it. So to say it's reducible means we can factor it into a product of two polynomials, right? They can't be just numbers. They have to be either linear or quadratic, right? And so the quadratic will factor into linear times linear. The cubic will factor into linear times quadratic. I mean that. So if it's reducible, then it has a linear factor. However, factor theorem says x minus, x minus a divides f of x if and only if f of a is equal to 0. So that's the proof, which is exactly the logic we just used in example 4. See, to each 0, there corresponds a linear factor. So if there is no 0, there is no linear factor. And if there's no linear factor, there's no factoring at all in this degree 2. Now, I said don't overextend this. Let me show you how you overextend it, okay? Example 5, a cautionary tale. F of x equal to x to the 4th plus 14x squared plus 49. So this is exactly x squared plus 7 quantity squared. So if we think of f of x as an element of polynomials over R, then there does not exist, C in the reals such that f of c is equal to 0, right? This polynomial has no real 0. And yet, what did I just do? I just factored it, right? I just showed how it can be reduced. This is a reducible polynomial, right? F of x equal to x squared plus 7 times x squared plus 7. Are either of those units? Nope, not units, right? Not units, and we factored. It's reduced. Now, you can prove that x squared plus 7 is irreducible over R, right? Since, x squared plus 7 equal to 0 has no, real solution, right? X squared plus 7, that's a second degree polynomial, which is non-zero, no matter what real number you put in it. Therefore, by this theorem, it's irreducible. Because if it's not reducible, then it's irreducible. Yeah, but it stops working at order 3. Because at order 4, it could factor into quadratic times quadratic, right? So you can't count on there being a linear factor to use the factor theorem to get the 0 for, is what happens. All right. So I really, I need to kind of skip over a bit here, guys, because it is, well, let me just tell you this. It would be good for you to read page 149, 150, and 151. What I'm skipping over here is the theory of primitive polynomials. And so the primitive polynomial is, the concept of a primitive polynomial is something we can use to study irreducibility of polynomials with integer coefficients. But I'm not terribly interested in that at the moment, and I think it will if I cover that, it's going to make me hurry through something which I would rather do slowly. So I'm just going to leave that to you guys reading, but that is the discussion which actually proves. Well, let me just tell you what. Let me just try to steal the major theorem from that section rather than proving it. How about that? Yeah. I won't prove it. I'll just state it. That's how we can have our cake and eat it too. I've actually already. This is something you've already seen back at the start of the course. I had a homework problem about this, I think even. But here's the theorem. 4.6.13. Let P in Z be prime. All right. And suppose f of x in Z, polynomials over Z, right, has degree larger than or equal to 1. Consider f of x with a bar over it, the corresponding polynomial in ZPX. So I think I used a different notation in the homework, but I basically set this up in one of your homeworks, right? I talked about how to take a polynomial with integer coefficients and find the corresponding polynomial with Z mod n coefficients, all right? And so this is the corresponding polynomial in ZPX formed by reducing coefficients of f of x modulo p. All right. Here's the kicker. If f the reduced polynomial, if f bar of x is irreducible over ZP, and the degree of f of x bar, excuse me, the degree of f of x is equal to the degree of the reduced one, all right, then f of x is irreducible over the rational numbers. So this is a very nice theorem to use, but I'm just not interested in its proof with you guys, if you'll forgive me. I hope you can forgive me for not proving it. Example 6, I'll apply it at least, though. That's worth our time for sure. F of x equals to 29x cubed plus 5x squared plus 2x plus 1, right? Mod 2. F of x bar is what? So reduce those coefficients mod 2. What do you get? You get x cubed plus x squared. That's 0 plus 1. So that's the mod 2 reduction. So if we look at this as an element of Z2, is it irreducible? Right? It's cubic, so we can just check if it has a 0. In Z2, there's only 2 things to check. right? F bar x of 0 is 1. If we plug in 1, we get 1 plus 1 plus 1, which is 1. Therefore, there's no 0. Hence, f of x bar is irreducible over z2. And notice that the degree of f of x is equal to the degree of the reduction, right? They're both 3. Therefore, f of x irreducible over the rational numbers. This is very, very nice because like directly proving it's irreducible over the rational numbers is not something you really want to try on for size. You might wonder where this bag of tricks comes from. The one, the only, you guessed it. Well, actually, you guess it. Who'd you guess?
Like who?
Who do you want to guess?
I'll guess a gas.
Ah, that's a good guess. I would say you either guess Euler,
Yeah.
you guess Gauss, or you guess Euclid, yeah, maybe. Or maybe Lagrange, I don't know, but yeah, it's Gauss. So at least Gauss discovered it. Did other people discover it? Probably. So anyway, there's an example of this. I have another example in the notes. I should warn you, cautionary tale. By the way, f of x equal x to the 4th plus 1 has f of x bar in ZPX reducible for all primes. Yet f of x is irreducible over Q. What this says is that the example above works when it works. But if it doesn't work for all possible primes, that does not allow you to conclude that irreducibility, that reducibility necessarily follows. Woe to the abstract algebra students that are assigned this problem. Woe to them. I have assigned this. Maybe I'll assign it to you guys. This one. I don't know. I feel like this might be the hardest abstract algebra problem I've ever assigned in terms of just, it's just gory. But it is a good exercise. I mean, if you work your way through that, you've really learned a lot. But anyway. Uh-oh. Well, I haven't erased anything that I have. It's okay. I haven't done anything. I was just writing over here and not focused over here. Not that I've... You guys are both here. What do you care?
No, there's the unsung hero watching us in the future.
Yes, here. Yeah, this is true. All right. Okay, so next. And this is another thing I won't prove, but we'll use, theorem. This is called Eisenstein's. Criterion. Let f of x equal a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, plus plus a0 be a polynomial with integer coefficients. All right. If there exists prime p in Z, of course, such that, get this, P does not divide A sub n, does not divide the leading coefficient, but P divides A sub j for j equals n minus 1 all the way down to 0, then f of x is irreducible over Q. Now, this is one of those theorems. So this is like the most basic version of this theorem. My brother was just commiserating that, you know, he can never figure out what generality to state this theorem in, because this theorem has more abstract versions. But this suffices for our purposes in here, okay? And if my brother writes up a little thing on the more general and abstract way of thinking of Eisenstein's criteria, I'll pass it on to you guys. Seems like it's on his mind at the moment. But anyway, like I said, I'm not going to prove this. There are various proofs of it. Some of them are easy. Some of them are easy later on, but I'll give you an example, though. So this is one of those results that's very nice to know. Very nice to know for like the subject test and the math GRE. This is the kind of weapon that you can attack if you have a question about, like, is this an irreducible polynomial? This is one of your go-to tools. But you notice in order to apply this weapon, you have to make a choice of the prime to look at, you know. Although I think oftentimes after you see the polynomial that you're looking at, the prime to choose, it just kind of stares at you and goes, oh, okay, obviously I'm going to use P equal to whatever. So I'm going to write this down, and you guys tell me what P I should use. Is this irreducible over Q is the question, over the rational numbers.
You gotta find a P to modify.
We need to find P so I need to find a P which does not divide 13, but P divides 2, 4, 18, and 2 itself, right?
Yeah, 2.
So obviously choose 2, right? Choose P equals to 2 by Eisenstein, f of x irreducible over Q. Okay. Ta-da! See, that's not so bad, is it? Yeah. Well, yeah. One of my favorite YouTube comments was like it was an abstract algebra 2 class, and I was deep into Galois theory. All right, and so Galois theory is something that happens after everything we're doing here. It uses fields, it uses groups, it's all together. It's quite abstract. It's really the crowning jewel of the undergraduate abstract algebra course, if you can get to it. Not everybody does. Most of the books have it in there, so apparently people think it can be done. Many people have decided that it's a fool's errand with undergraduates at their institution to attempt it. So it's anybody's guess as to whether or not you pick a given undergraduate institution, you can actually study Galois theory at the undergraduate level. But anyway, so I'm giving this Galois theory lecture, and I had a high school student visit. And so in the middle of this lecture, I'm saying all of this really like lowbrow stuff about quadratic equations. And I had YouTube comments were like, you're being very condescending to the students. Like, these are abstract algebra 2 students. You shouldn't talk to them like they're high school students. Which is like, but there was a high school student there. I don't know. It amused me. I have to remember the Aldrich standards for comedy are always high, but when he's sleepy, they're even higher. So,
No, I've been standing for a while, so the plug got out of my brain.
So let's do some algebra.
I think that's how that works. It removes goes to memory and away from memory and saves
1 plus x to the p minus 1. All right. And if I do x times s, I get x plus x squared plus da-da-da plus x to the power p, right? And if I do s minus xs, I get, well, everything cancels, right? Except for x to the p. Wait a minute.
And 1 when it's not canceled. All right, let's make this rewrite it.
I just wrote them in the auto. It's just a typo in the notes. This gives me x to the p minus 1, right? So what we have then is x minus 1 times 1 plus x plus da-da-da plus x to the p minus 1, right, is equal to x to the p minus 1, which then suggests the following, that 1 plus x plus da-da-da plus x to the p minus 1, we can look at as x to the p minus 1 over x minus 1. All right. And this guy right here has a name. This is big phi p of x. This is the pth cyclotomic polynomial. Theorem. Phi p of x, irreducible over q for any prime p. So this is a sneaky trick here. Let f of x be equal to phi p of x plus 1. All right. Then by the formula above, this is what? X plus 1 to the p minus 1 over x plus 1 minus 1, right? So I'm using star, just replacing x with x plus 1. But then what?
You get x plus 1 to the p minus 1 over x.
Yeah, so I'll put a 1 over x out front, right? And like you said, x plus 1 to the power p minus 1, right? So what is that? Well, that's 1 over x. Ah, yes. So that's 1 over x, yeah, times x to the power p plus p, x to the p minus 1, right? Plus p, choose 2, times x to the p minus 2, plus da-da-da-da, plus eventually you get to 1 to the p. Well, I'll write the 1 right before that. Then you get p x plus 1 minus 1. So I'm using the binomial theorem. So the coefficients in the binomial